Nice. So uh, we are going to talk, as I said, about electric, not electrical, electric. Okay, electric conductors. Okay. Okay, let me just close some of the programs because the stuff still it's like it's very okay. Now okay, iTunes, I should close it. I should close iTunes. But why? Okay, I should close iTunes. Microsoft Excel, OneNote, no. QView Player, no. R, yes. So Forskit from this three. Forskit. Now let's close also VLC. Inference. Safari and Arable Reader. No, Safari I keep no, yes, we close also this one. Okay, let's close Forskit. Nice. Okay. So let's talk about electric conductors. By definition, so we start by the definition. What is an electric conductor? Definition. So an electric conductor, okay, is any matter or any solid, any matter in which the charges are free to move. Okay, an electric conductor is any matter in which the charges are free to move. Okay, so as we will see in the next lecture, there are electric conductors and there are dielectrics. Okay, in the dielectrics we will see that the charges are not free to move. So this is the main difference between electric conductors and dielectric. These charges are free to move typically due to what? So if you have a conductor like this, let me draw a conductor. If you have a conductor that may be anything like this, and if you have an external field, so you have this is the external part of the conductor, right? If there is some external field, then as the charges are free to move inside the conductors, then the charges inside this conductor are expected to move because you have some external field. Now, but when we in this chapter we are going to talk about electrostatic field. So if we are talking about the electrostatic field, what do we mean? We mean that the charges are not supposed to move. Okay, so what should I do? What should happen in order to make sure that the charges in the conductor are not moving? So what we want to do is to analyze the structure of the field when we have equilibrium. Okay, when we have electrostatic okay, when we are in electrostatic conditions. So suppose that we have a conductor here. We know that by definition the charges are free to move. There are charges inside, and there suppose that you have charges inside the conductor. Okay, if the electric field inside, if the electric field here inside is not equal to 0, to the null vector, because I remind that the electric field is a vector at each point. If the electric field is not equal to the null vector, what happened? It happened that the charge inside the conductor will be moving. Okay, so turning back about, I said, for example, if you have an electric field outside, so remember that when you have an electric field, it is applied everywhere. Imagine I put a charge Q here, and I put a conductor, and I draw a conductor like this. This charge Q create the field everywhere, even here. No, why? Yes or not? In fact, is that clear? So when I put a charge Q, it will create the field everywhere in the space, and that means, and if I want, and as this stuff is as this is the conductor, okay, if we assume that there is also the charge, the field is also, if there was a field here inside, okay, the charges, as they are free to move, the charges of the conductor are free to move. So if there is a field in the conductor, then the charges of the conductor will be moving. As we don't want that to happen, we don't want the charges to move. Why? Because we are doing electrostatic. Okay? So if you want the charges of the conductor to be in equilibrium, the only thing that we can do in order to make the charges of a conductor to keep the charges of a conductor in equilibrium is to make the field inside the conductor should always be equal to 0. This means that even if I put a charge Q outside, and if this stuff is a conductor, even if there is some field outside, the conductor will maintain the field it's inside equal to 0 in order to stay in the equilibrium condition. Yes. Can you repeat your question, please? Is it what? Yes, but this is a conductor, yes or not? But this was in the general case. Now I am telling you that a conductor is supposed to keep the field. I told you that this is what you expect to have, yes or not? This is what you expect to have. But I am telling you that in real life, to maintain the equilibrium, so to keep the charge fixed, okay, to keep the charge fixed, the field inside the conductor should be equal to 0. Otherwise the charge will be moving. Why do we want to keep the charge fixed? Because we are doing electrostatics. No, they stay fixed. Now I am going to explain. So I talk about the field in the we understand that in equilibrium, okay, in equilibrium the electric field inside any conductor, okay, is equal to 0, to the null vector. Okay, I repeat, because if the electric field wasn't equal to 0, this electric field will move the charges inside the conductor, because by definition the charges are free to move inside the conductor. Now, what happened to the charges? The question will be, now, if on the surface, what is the value of the electric field on the surface of the conductor? We understood that inside the field is 0, but how will be the electric field on the surface? Let's go down and draw once more a conductor. We understood that the electric field inside, in the equilibrium condition, the electric field should be the null vector, otherwise the charge inside will be moving. Now, what happened? Yes. Okay. The question is the following. I said at the beginning that the conductor is any matter in which the charge is free to move. The charge are free to move if there is a field accelerating them. Is that clear? But if there is no field accelerating the charge, they will not move. So we are saying that what happens if you take a conductor in equilibrium? A conductor in equilibrium means that the charges on that conductor are not moving, and for this to happen, the internal field should be equal to the null vector. So this is not in contradiction with the definition. The definition says that the charges are free to move, but to move these charges you need a field. But if you want, I am saying that if you want the conductor to be in equilibrium, okay, being in equilibrium means to have electric equilibrium. You have the charges. If you want the charges of the conductor to be fixed, because they are free to move, but if you want them to be fixed, the internal field, the field inside the conductor should be equal to 0. Is clear now? Now, I would like to understand what is the implication of the. So if I put, if there is some field outside, okay, what happens to that field at any point of the surface? Look, I will say that the field at any point of the so if you take the surface of the conductor, the field at any point of the surface of the conductor should be perpendicular to the conductor. So the field at any point of the conductor should be perpendicular to the conductor. Why this should happen? Imagine, for example, that to explain this, let's take a conductor that has a rectangular shape. Let me attach the PC. Remember that we want to keep the conductor in equilibrium. In that we want to make sure that the charges will not be moving. So if the field is perpendicular to the surface like this, yes or not, there will be this field can just move the surface, can move the charge only in this direction, yes or not? But if the charge go inside, as soon as the charge enter, there is no more field, so it stop. So when the field is perpendicular, this field will try to move the charge inside, but as there is no field, as there is no electrical field inside, the charge will not move inside. Okay? But if the field wasn't perpendicular to the surface, of the conductor, so let me draw a field that is not perpendicular to the surface of the conductor. So maybe the field come like this. So this is the field, the external electric field. This field that if the field is like that, you can split it in two components. There will be the tangent component. So this field that come like this, this field can be split in two components. There will be the you can split this field like this. There will be the tangent component and the normal component. Yes or not? And thus this component here, if there are some charges on the surface of the conductor, this component will move the charges on the surface. Yes or not? This component of the field, this one, will move the charges on the surface of the conductor, and we don't want the charges on the conductor to move. To summarize, we say that 1, by definition, the conductor is any matter in which the charges are free to move. Okay, this means that if you want to keep that charges fixed, the field inside the conductor should always be equal to the null vector. Then we saw that if there is an external field, this field should always be perpendicular to the surface of the conductor. Otherwise, the charges on the surface of the conductor will move. Is all clear? Okay. This tell you that for sure tell you that the conductor, when you have a conductor inside a field, so when you put if you have a field like this, you have a field, you put a charge Q, for example, and this charge Q creates some field. Okay, if you put a conductor inside, if you put some conductor inside, the field in this part the field will disappear inside. If you put the conductor inside and this conductor is in equilibrium, the field here inside will become 0. Is that clear? Doubts? Okay, if there is some doubt, can I is there any question? When I say conductor in equilibrium, means that the conductor in which the charges are not moving. Conductor in equilibrium means that the conductor on which the charges are not moving. In fact, that is what happened. I want to put the conductor in a field in such a way that its charges are not moving. And your question is, yes. In fact, okay. Also because you say, good. What happened in the nature? The system always arrange itself in order to, any system, even if when you change the equilibrium position, when you take the conductor at the beginning, the charge, if there is no field and you put it inside a field, the conductor will arrange itself in order to turn back to an equilibrium position. Yes or not? So if there is a way, so any physical system, if there is a way for this system to turn back to the equilibrium position by itself, it always tries to turn back to such a position. Yes or not? So if I take this conductor and I put it inside a field, it's clear that maybe at the beginning the charges in the conductor will be moving, but the system will be trying to turn back to the equilibrium position, and that is why when the equilibrium position will be reached again, okay, the field inside the conductor will be 0, and the field outside on the surface of the conductor will be perpendicular to the surface. Is that clear? Okay. So I'm not saying so when you put the conductor inside an electric field, okay, the conductor make the field in the internal field equal to 0, the field inside the conductor becomes 0, and the field the field on the surface become perpendicular to the surface of the conductor. All this to reach the equilibrium, to make sure that the charges will no more be moving on in the conductor. Is clear? Okay. So this tells us that the conductor modify the property of an electric field. When you put the conductor in an electric field, you change the property of that electric field. Yes or not? Okay. So let me summarize the thing that we saw so far. So one, the electric field inside the conductor is equal to the null vector when the conductor is in equilibrium. Okay. Two, the electric field is perpendicular to the surface of the conductor, okay, when the conductor is in equilibrium. Okay, nice. So turning back to the definition of conductor, all this we are doing all this stuff just because the charges are free to move inside the conductor. Okay, if the charges wasn't free to move inside the conductor will not have the possibility to react, because when you say okay the field will be 0, it just means that the conductor arrange the charges in such a way that the total field inside is equal to 0. Okay, nice. Now we continue. Okay. Now, what happens if you put, so if I give you any conductor, if I give you any conductor like this, how much what is the total charge on this conductor? So yes, even if the total charge, okay, the total charge on any matter, on any neutral matter, is always 0. Yes or not? Now suppose that I have this conductor, okay, the initial, so when I give you a simple conductor, the total charge on it is 0. But now I take the conductor, if I put some excess charge on a conductor, so I take this conductor and I put on it some charge like this, some positive charge in it. Is that clear? What will happen to this positive charge? In order to reach the equilibrium, if I keep this positive charge inside the conductor, what will happen? This positive charge will create an electric field inside the conductor. Yes or not? Because when you put the charge somewhere, it's supposed to create an electric field. But in order to reach the equilibrium, what will happen? These charges will move to the surface. Okay, these charges will go on the surface. It's clear or it's not clear? So if you put some excess charge on a conductor, these charges, in order to reach the equilibrium, the conductor will distribute this charge on its surface. Why this hole? Because I told you that if this charge remain in, the internal field will not be equal to 0. The internal field will be 0. If the charges go on the surface and arrange themselves in a particle, because now look, what is the question? I told you that anytime the conductor is in equilibrium, the internal field should be 0. What am I saying? Look, if I have these charges inside, you remember the Gauss theorem, right? If I have charges inside and I draw a surface like this one containing these charges, so this is not the green surface is not the surface of the conductor, but it is any geometrical surface. The Gauss theorem tells us that the flux, like if I do the flux, that is the integral of A dot the normal vector, right, in ds is equal to the total internal charge divided by epsilon 0, right? This is my surface S. This surface is S. So the flux through the surface S of the field is equal to the internal charge divided by 0. Now, as the internal charge is not 0, because look, the internal charge to the green surface is not 0, yes or not? This means that as the internal charge is not 0, this means that this flux is not 0, yes or not? And if this flux is not 0, it means that the electric field inside is not, the electric field on this surface is not 0. Yes. Yes. But if the charge is 0, then the electric field will be, okay? In fact, if Q in is 0, the flux will be 0, and thus the electric field will also be 0. Is that clear? Questions? That's why, in order to make sure that we don't have electric field, if you put the charges inside a conductor, the conductor, in order to reach the equilibrium, should push out all these charges and put it on its surface. Is that clear? Because if something remains inside the conductor, by the Gauss theorem, you understand that the field inside the conductor will not be equal to 0. Okay? So this is another property of conductors. I told you that this is typically a theoretical lecture. So the next property, another property, the fourth property that we discover is that if you put some charges inside the conductor, so charges, okay, if you put charges inside the conductor, such charges, okay, will move to the surface at the equilibrium. Okay, nice. So this is another property of the conductor. Nice. So we are just, this is I think the fourth one, because the first property we saw was that, no, the third one. The first property was that the electric field inside the conductor is always 0 at the equilibrium. The second property was that the electric field is always perpendicular to the surface of the conductor. Now the third property is that if you put any excess charge inside the conductor, then at the equilibrium such excess charge move to the surface of the conductor. Is that clear? Now we are now going to analyze the last property of conductors. Okay, any question? Okay. I am coming. Last property of conductors is the following. Now yesterday in the lecture of yesterday, I told you that we saw that the electric field is equal to minus the gradient of the potential. Okay, just to remind and to refresh, it's this I say what it means. If the potential is the function v of x, y, z, so the potential at any point is, for example, x squared plus 2x, y, z minus y. What will be the field? The field is minus the gradient. Minus the gradient means minus the derivative of v with respect to x, minus derivative of v with respect to y, and minus derivative of v with respect to z. Okay, this is the meaning of minus the gradient. Okay, so for if the electric potential is like this, the electric field at any point will be this vector, will be the derivative of v with respect to x will be 2x plus 2y plus 2yz, so it will be 2x minus 2x minus 2yz, comma the derivative of v with respect to y will be 0 plus 2xz minus 1, so 0 plus 2xz minus 1, and the derivative of v with respect to z will just be 2xy. Okay, so this will be the electric field. Now there is minus, and here there is also minus. It's multiplied by minus. I forgot the minus. Okay, so to write it down, the electric field at any point x, y, z will be equal to minus 2x minus 2yz, comma minus 2xz plus plus 1, comma minus 2xy. Okay, so this is how the potential and the relationship between the potential and the electric field. Now let's try I just remember this relationship because I am going to use it now for the conductor, on the conductor. So let me take a new page. So let's draw a conductor and try to understand what happened about the potential of the conductor. We know that for a conductor, the electric field inside the conductor is equal to the null vector. Okay? So we are just saying that the electric field is equal to 0, 0, 0 everywhere inside the conductor. Nice. What will, if the electric field is 0, 0, 0, what does it mean? It means, I remember that the electric field is nothing else than minus the gradient of V. Okay? So as the electric field is equal to the null vector, this means that minus the gradient of V is equal to the null vector. Okay, minus the gradient of the potential. But the gradient of the potential equal to the null minus the gradient of the potential equal to null means that minus the derivative of V with respect to x is 0, minus the derivative of V with respect to y is 0, and minus the derivative of V with respect to z is 0. So the derivative of V with respect to x is 0, the derivative of V with respect to y is 0, the derivative of V with respect to z is 0. This simply means that the function V is a constant, yes or not? Because the only way to have these three stuff is that the function V is a constant, because the derivative of V with respect to x equal to 0 means that V do not depend on x. The derivative of V with respect to y equal to 0 means that V do not depend on y. V doesn't depend on y. The derivative of V with respect to z equal to 0 means V doesn't depend on z. So the only way for these three stuff to happen is that V is a constant. So we prove that the potential inside a conductor, okay, the potential inside the conductor, the potential inside a conductor, okay, in equilibrium is constant, is the same everywhere, okay? Saying that is constant means that the potential is the same everywhere, yes or not? So when I take a conductor, at each inside this conductor, the potential everywhere is the same. If the potential everywhere is the same, now what happened? I want to say is that we are doing physics, we are not doing mathematics, okay? You cannot, if you have that the potential, suppose that I give you this conductor, and here we prove that here inside the potential everywhere is the same, is constant. Suppose that the potential here everywhere is the same and it is constant. It will mean that the V, suppose for example that the potential is everywhere the same and it is equal to 5 volt. Is that clear? Up to you, what will be the potential on the surface? What will be the value of the potential on the surface? No. At any time, this conductor is in equilibrium. If I am saying what will be the value of the potential on the surface of the conductor? Yes, exactly 5 volts. Okay, because the potential should be the potential is a continuous function. Okay, we cannot move from 5 volt directly to another value without a transition. Yes or no? Even if it is not exactly 5 volt, it's not far from 5 volts. Okay, so we just proved that. So also on the surface the potential will be exactly 5 volts. So what is our fourth? So that the fourth property that we prove is that a conductor, any point of the conductor has the same potential. Okay, any point of a conductor has the same potential. Any point of the conductor has the same potential. That is why we talk about when we talk about the potential, we say that a conductor has a potential of 5 volt. A conductor have a potential of 10 volt. Okay, So don't be surprised if I talk about the potential of a conductor, because by the way, a conductor in equilibrium has always any point of the conductor will has the same potential. Okay. Nice. Now we conclude our lecture by talking about the hollow. Okay. No, the hollow conductor. The hollow conductors are conductors with a cavity. Like when I give you a conductor like this one. So this stuff is a cavity. So this is empty. This is not a. I mean, the surface of the conductor is made by. The surface of this conductor is made by this surface. I mean this one. Okay. And this one. No, 2D. It's like a ring. Okay, kind of ring. So this okay. So what is the, if I have a conductor like this one, the surface of this conductor is made by how many circles? 2 circles, right? This is the center. Okay, this is now suppose what is the internal, if I have a field, imagine I put a charge Q here outside. What is the internal part of this conductor? The internal part, very pay attention to this. The internal part of this conductor is just this. Yes or not? So the field here, turning back, the field here in this disk, the field will be E equal to 0. Yes or not? To the null vector. But yes, I agree with you. But in the exercises, normally one should say, okay, when the conductor is in equilibrium. But in this, in the course of physics 2, when you talk about conductor, we implicitly assume that the conductor is in equilibrium. Then, but the field here is not necessarily equal to Z. Yes or not? No, even if there are no charges, even if there is just this charge here, even if there is just the charge Q, the field here, because this is not the internal part of, this is not internal, but pay attention. By the way, no problem. Is there any question? The charges will go to the surfaces on the body of the body. Yes. Now I will explain you what happened, but this charge is external, not internal. Yes or not? Now I told you. Now okay, the question here is that I am saying, is this E equal to 0, C or no? I mean the electric field in this zone here. I know that this zone is not the internal part, it's not internal to a conductor, but I want to know the E in this zone here. I want to know, is this E equal to 0 or this E not equal to 0? As your question, look, I told the Gauss theorem is very important because it gives you the possibility to answer to this kind of questions. Look, if I take, let's draw again the conductor. We said that we put a charge Q outside, yes or not? You want this charge Q will create a field. We know that the field here, because this is the internal part of the conductor, the field here will be 0. But our question is, what about the field in this zone, in the green zone? Now let me put Let me put the green. What about the field in this green zone? Okay, look, you know probably that if I take the chart, if I take the any if I take, for example, this surface here, this is a closed surface, yes or not? What is the flux through this surface? The flux through is integral of E dot M in ds, yes or not? But how much is the field at any point of this surface, of the black surface? What is the value of the field at any point of the black surface? How much is the value of the field at any point of this black surface? Yes or not? It has to be 0. It's clear? It will be 0 because this black surface is inside the conductor. At any point the field here is 0. So this flux, this integral will be 0 because it will be the integral of 0 multiplied by n. But we know that this integral is q in divided by what? Epsilon z. This means that we have 0 equal to q in divided by epsilon 0. What is the meaning of this, Tiger? It means that the total charge inside this stuff, this surface, is expected to be equal to 0. Yes or not? But in fact, we don't have any charge inside. My question was about the field. But suppose now we don't have any charge here, right? Okay. This means that we cannot have a charge here. Now let me take any other surface which is green, but here. We already proved that we don't have any charge inside in the green zone. Now, as we don't have any charge in the green zone, if I take a green surface, a gray surface like this, there is no charge in this gray surface. So, if I do the flux of the field, in ds, this is multiplied by n in ds on the green surface, it should be equal anytime to q in to the internal charge divided by epsilon 0. But the internal charge in the red surface is equal to 0. So the flux, the flux of E in ds through any surface, so the flux of the field through any surface, okay, any closed surface here, is always in this zone. If I take any closed surface, the flux of the field through such any closed surface in this zone will be always equal to 0. Is that clear? Doubts? So this is what we can give about the property of the field in this zone. This does not prove that the field is 0, but it proves anyways that the flux of this field through any closed surface should be equal to 0. Now let's see the last thing we see is what happens if we take a conductor with a cavity and we put some charge inside. This was so suppose I take a conductor like this with some cavity and I put a charge, and I go here and I put some charge Q here. Now we know that whatever we do, that we should arrange the charges such that the field here give what? Give 0. We should arrange the charge such that the electric field here gives 0. Now, what will happen if we put this charge? Suppose that this charge is positive. So if we put some charge, a positive charge in the middle like this, it will happen something very nice. It will happen something very nice in the sense that if you put if nothing happen, so let's draw again. I put that charge. No, I will not draw again. It's if I put this charge, and if nothing else happen, let me draw any black surface like this. We know that the flux the flux through the black surface, yes or not, should be equal to the internal charge of the black surface divided by epsilon 0, yes or not? And thus this will mean that the flux through the black surface, what is the internal charge to the black surface here? What is, no, not 0. Look at this black surface. The internal charge will be Q. No, the internal charge will be, because I put the charge Q here. No, but look, in this case, the charge Q is outside. Look at what is the black surface? Now, I am saying what is the, I took this is no more the conductor. I am talking about the internal part of this surface, the internal part of the black surface, the geometric surface, not the conductor. What is internal to this black surface? It's all the part which is internal. So you should what the ring is a conductor, but this black surface is a geometric surface. When I draw any geometric surface like this, the internal part of the surface is all this. But if I tell you that if I have a conductor which has a form of a ring, the internal of this conductor will be only this part. Yes or not? But when I draw the conductor will be in equilibrium. If I put the charge Q plus inside, I am now analyzing what happens if I put a charge Q inside a conductor. No. Okay. When I say inside the conductor, I mean inside the cavity, not inside the conductor. This charge is inside the cavity. Okay. No, but it's external to the conductor, but not external to the black surface. Yes, it's clear. So, yeah. In fact, when I draw a black surface like this is a black surface. It's a surface. So its internal is this stuff. No, okay. So because the Gauss theorem applied to any closed surface. So I draw my closed surface, and I'm saying that the flux through this closed surface, so it will be the charge Q, the internal charge to this closed surface will be Q. Yes or not? Divided by epsilon 0. Now you see that. So if nothing happen, I will get that this flux is not equal to 0, because this charge Q is not 0. And this will, if this flux is not 0, it means that the charge, the fill on the fill on the surface is not 0. Yes or not? And if the fill on this surface is not 0, it means that the fill here is not 0. But this is a contradiction. Is clear or is not clear? So when I put this charge inside, so if the total charge in this surface, in the black surface, is not 0, the field on the black surface will not be 0. This means that anytime I put the charge in the cavity, so let's draw again the stuff. Let me take a new page to make it more clear. New page. So anytime this is a conductor, if I put a charge Q plus here, what will happen? Please let make it big so that we can do all our interpretations. I take a very big conductor. Okay, now if I put some charge Q here and it is positive, what will happen? It will happen that we saw that if the stuff remain like this, it is impossible for, if the stuff remain like this, the field here will not be 0. Yes or no? The field in this part, if the stuff remain like this, the field in this part will not be 0 due to the Gauss theorem. Yes or not? But if you want the field here to be 0, we need, what will happen if you put a positive charge here? If you put as we put the positive charge here, the same negative charge will be distributed on this border. Is that clear? Some negative charge, but this negative charge will be exactly Q minus. Now, what will happen? So this charge will come from what? It will come from the inside of the conductor, from the interior of the conductor. Is that clear? Now you know that the conductor, if you move, so this means that as this charge Q minus comes from the inside of the conductor, any electron that goes out will make free a proton. Yes or not? Because in the conductor, any charge, any electron should go with a proton. Yes or not? Because the matter is always neutral. Yes or not? So if you move an electron and put it on the surface, so if you move this electron, you make one proton free. Yes or not? So if we move this charge Q on the inner surface, some protons will be free, and we say that any free charge in the conductor move to the surface of the conductor. As we exactly move a charge Q minus to the inner surface, a charge Q plus will move to this surface. Is that clear? Now let's see if all the stuff works. Now let's check if the field let's check now if the field here is Z, is the null vector. To check that, we use the Gauss theorem. Suppose that I draw any closed surface like this. At any point of this closed surface, I want the field to be equal to the null vector. Yes or not? At any point of this closed surface, I want the field to be equal to the null vector. At least if you try to do it with the Gauss theorem, if you do the integral of E dot n ds on this surface, so I am still asking if this is true. It should be equal to Q to the internal charge divided by epsilon 0. But now, what is the total internal charge to the black surface now? You have the Q plus and you have Q minus. Yes or not? So the total internal charge is Z, Okay, so the integral of E dot n in ds, okay, is equal to 0 because the internal charge is 0. Yes or not? Now, as this happen for any you can take any surface you want. As this happen for any surface, it means that the E is equal to 0. So in fact, by putting the charge like this, the field inside is always equal to the field in the conductor will be 0. Yes or not? But you say, but in fact, if you sum up all the total charge, you see that you get, because this charge here die with this one. Yes or not? But the remaining charge is anyway Q, because at the beginning you cannot create the charge, you cannot destroy the charge. It means that when you distribute the charge on the conductor, at the end you should make sure that the total charge that you gain is equal to the initial charge that you had at the beginning. Is that clear? So this is more or less how the stuff changed if you put a charge inside a conductor. Okay, it will be the same if it will more or less be if you put a negative charge Q minus in the inner surface, you will get positive charge. Yes or not? To make it 0, and then outside you will get a negative charge. Doubts? I will give you an exercise. The exercise can be, maybe you have more than so the conductor is made by something like this. So you have the first, let me draw it better. Let me even take a new page for this. Okay, the exercise I want to give is the following. Your conductor, it's made by a couple of cavity, okay, and here in the middle you put some charge, let's say you put some charge 2Q, okay, which is positive. Okay, I want to know, you should tell me at every level. So this is level 1, this is level 2, this is level 3, this is level 4. At any level, what will be the charge that you will have? Okay, so I mean, this is your first conductor. This is your, yes, this is the first conductor, and this is the second conductor. So you should find the charge that we'll have at every level. Okay, now think about that, and you have to think about that, and we will discuss for the next lecture. Okay. Nice, but before we close, another exercise is the following. For the next lecture, is all another exercise for the next lecture is the following. Okay, you have a spherical conductor like this, okay, and with radius, let's say the radius of this spherical conductor is big R, and here I put another spherical conductor with radius, and the radius is small r, okay, and then I connect the two conductors together to make it a single conductor. Then I distribute some charge I distribute some charge Q. So I have some charge Q, okay, Q coulombs, and I put it on all the conductor. My question is, on which conductor there will be more charge? On which conductor there will be more charge? So yes, on this, because the conductor cannot stay inside the conductor. So on the surface of which of these two conductors there will be more charge. Is that clear? Okay, so next lecture, that is on Wednesday, we will typically in the next lecture on Wednesday, we will talk about resolve these exercises. Okay, nice. See you. Bye.